Sometimes I'm selfish, get jealous. I feel a little helpless. My whole world has shifted again. You made a promise, I kept it. Now I'm second guessing. My whole world has shifted again. Now I drive back to an empty home, and it's setting in. Now that you're there,
Good evening, welcome everybody. My name's Obi-Wan Piz. This is N-Simple Pachinko, and we're going to be doing some math tonight. So, my father is a woodworker, or at least, it's been a significant part of his life. And he asked me today if there was some way to create a thing, and I was like, well, absolutely, I'm going to just spend like a good chunk of my day trying to work this out. So his idea was that he wanted a shape that started with a rounded triangle like this. It has circles in the gross. Actual circles. In the corners, which will cause it to be rounded rather than standard polygonal. Yeah, okay. And then what he wanted to do, what the real, like, hey, you're a mathematician, why don't you try to figure this out, was he was trying to figure out a way to get, to get the inner circular radii to end up being some proportion of the distance between the outer edge and where he wanted to, like, sand off some, such that we will get a curve like this. Hence why I said, oh, well, it's sort of like a fidget spinner, essentially. And the first assumption was that this was going to be about like half the radius of the circles that were coming in, and so we'd end up with kind of this sort of shape to it. And so I gave him some ideas, and eventually we settled on a slightly easier solution, which may or may not be exactly what he wanted, but he seemed to be happy when I last texted. So he's also 5 hours back from me, so he may have been still working at the time when we were discussing it. It was around dinner here, so, you know, what, like noon, 1, 2, somewhere in that neighborhood. So the question becomes, what curves can we actually use in order to create something useful here? And, like, yeah, just what kinds of curves could actually make this work in the way that he set this up. So have a think about it for, you know, a few minutes here while we say hi. So, hey Famished, how's it going? Loving the solving equations by zero product property, because that's one of the best properties that you will stick with throughout all of your entire math experience. Like, if you can get that to happen, or if you could say, I know for a fact that this cannot happen, one of those two things is going to be fundamental in figuring out, like, I don't know, probably 60% of the problems that I've ever done. You know, at some point throughout its process. Hey Zach, how's it going? Jasu, welcome in. And last time we were actually talking about factoring. So this was, well, last week when we were talking about factoring. This is something that we use the zero product property for. So basically, we're going to assume ahead of time that our polynomial p of x is equal to 0, and then when we end up with p of x being equal to product of individual factors, right? In this case, we found out that this was going to be -4 for one of our zeros, which gets us an x minus -4, which is x plus 4. Right, so what would happen here is that we'd end up with this x plus 4 term, and then a bunch more stuff, and then we'd say, well, since we know that this is also equal to 0, then this product of stuff is equal to 0, and therefore our zeros for the function are going to be all of those individual pieces going across. Or perhaps we can reverse that and say, since we know that one of the zeros is -4, then we can build a polynomial that says our factorized p of x is going to be x plus 4 times all this other stuff, and that's going to be equal to 0. We'll do some more stuff at some point. But so, what is happening here? I mean, excellent question. So the top section is synthetic division, and we had done long division last week in order to show that synthetic division was so much superior. Because, I mean, look how much space this takes up, right? It's an entire page worth of stuff to do one division, to knock our 5th degree polynomial to a 4th degree polynomial. Now you got to go do it again, probably, because you don't know necessarily what the factors are going to be. It's not going to be obvious. We did come up with some assumptions that we thought -4, -3/5, and 1/2 were going to be zeros for this particular function based on the graph that we saw. And yeah, the graph we saw reflected that that was probably what those were. But you need to prove it. And in proving it, or in order to prove it here, what we can say is that what we know is that anytime that there's a 0, we're going to end up with a 0 for the remainder out here. Right? 0 remainder means that this is a factor and that this is a 0 of the function. So with synthetic division, we said, all right, take all of this stuff that we were doing here. We were taking these values. We were saying we're going to multiply them by x plus 4. We're going to multiply them to get this product down here, and then we have to subtract all of it. We know that the first two terms are going to cancel out to 0 because we engineered it that way. Right? That's the entire purpose. So we don't need to write all of this stuff. So if you know long division, it's actually pretty easy to get through and figure out what synthetic is going to be. So what we have is that, again, our first term is always going to end up subtracting to be 0. So we just kind of discount it and say, all right, we don't need to write it. The next part is that we are going to assume that we're going to write every single term of this polynomial in order, descending from highest degree all the way through lowest, all the way back to constants, right? So we're always going to write it down to constants. If we standardize it like that, then we don't need to write x to the 5th, x to the 4th, x to the 3rd, x squared, x, and x to the 0, or just leave it as a constant. We can instead just write coefficients. It works, right? Again, here, we already knew that this 10 was going to end up being our quotient term. Right? That's the whole thing. We know that it's going to be 10. So when we divide x plus 4 into 10x to the 5th, the first term is going to be 10x to the 4th in this case. Right, so that's another thing that sometimes gets overlooked just a little bit. Oops. Is that we already know that this is going to be, again, x to the 5th. This is going to be x to the 4th. And our term over here is going to be x minus negative 4. I mean, sort of. It's a tableau. So we're making a, like, table of values, essentially, that's showing us what the process is going to be without necessarily showing every single step. Wow, that sounded Canadian. I'm not from Canada. Okay, so then what happens, we said over here, what we're going to do is every single time that this, this term subtracts out, we get nothing. Then over in this term, where this comes from, is that 10 from the quotient is going to be multiplied by the plus 4 right here. And then it's going to be subtracted. So if we multiply by 10, we get 40, and then make it negative, it's going to be a negative 40. And again, we know that that's going to be the case all the way down this tableau here for our long division. We got a negative, and a negative, and a negative, and a negative, so it's always going to switch the sign. Whatever else is going on, it switches the sign. So we take the 0, x equals negative 4. We pop that out here, and that's going to be our reference. And we take the 10, we multiply it by negative 4, and now it becomes negative 40. And then we just add them. 41 plus negative 40 gets us 1. And by the way, right, that 1 is now here. Plus 1 x to the 3rd. It's the next term down. Right, so x to the 3rd. Hey, Jay McCallis, how's it going? So then we do the same thing. We say we're going to take our 1x to the 3rd, we're going to multiply it by the negative 4 up here, and it's going to get multiplied up this way to become negative 4. Then we just add. Negative 29 minus, or plus negative 4 is a negative 33. That becomes our x squared term. Oh, would you look at that right there. Right? Negative 33x squared. Again, this multiplies to the first term with our x and just becomes negative 33x to the 3rd. We're subtracting it out. We already know it's going to go away. It becomes 0. Done. But then the next term over again, we multiply by 4. Negative 4 being our 0 up there. Right? X equals negative 4. It becomes a positive, because again, minus negative 132. And we add 132 to the next coefficient, which was negative 135. So it becomes a negative 3x. Multiply that by negative 4, it becomes positive 12. Add negative 3, it becomes 9. Multiply by negative 4, it becomes negative 36. Add to 36, and it becomes 0. And again, as long as we have a 0 that we're looking for, in this case, x equals negative 4, then when we divide it all out, it's gone, right? All of our remainders clean up at the end. So we end up with a 0 here, and now this becomes 10x to the 4th plus 1 x cubed minus 33x squared minus 3x plus 9. End it, right? Because we've got a 0 here. We don't have any remainder. Then, and here's the benefit of doing synthetic division, especially over long division. The other fact is that we can now take the next number, which we said was, let's do negative 3/5. Okay, so I lied. We're just going to do this. All right, so x equals negative 3/5 is going to be... I want to put that up here. Is going to be applied to the quotient from the previous division, so it's this one, which means that we could just immediately write everything one line down. Don't have to recopy it, don't have to like... And that's the other thing with long division, right? Is that we'd have to take this quotient that we have up top here and write it in its own division sign because everything's in the way. We can't just like... we could do 3D graph paper or 3D note paper and pop it up one level. But, you know, we still can't do anything with it, really. Tiring 2 days in the office, extra long day today. Oof, sorry. But good on you for getting the math done. When I was doing my master's, I was also working a 30-hour-a-week job and also teaching 1 or 2 classes, depending on what was... pretty much what was happening is either I was teaching or I was taking, or the sum of them was 2. So there were always 2 classes that I was working on. Again, whether teaching or taking it. Okay, so we take our 3/5. We say that our 10 is going to come straight down. No effect, right? Because the placeholder here is a 0. So we add the 0 to 3, add the 0 to the 10. Nothing happens. So then we take this 10, we multiply it by negative 3/5. This is where it gets slightly annoying. There's going to be some fractions as we go through, but it's fine. Okay, so negative 3/5 times negative 10 is going to be a negative 6. Yeah. And we add it to 1, and that now becomes a negative 5. We multiply, okay, so it may not be that bad. We multiply it by negative 3/5, it becomes a positive, in this case 3. Add it to negative 33, becomes negative 30. Multiply by negative 3/5, again 5 is going to divide out, becomes 6 times negative 3. Nope, these are both negative, so it becomes positive. 6 times 3 is going to be 18, minus 3 is 15, divided by 5 is 3, times negative 3 is negative 9, and bingo. Okay. Here's the other thing about synthetic division. Right, we took out x plus 4 from this term. We took out, this is important, we took out an x plus 3/5 here. This is not how I ever format things. This is, I will never format anything as x plus 3/5. I hate it. I want everything to be integers as much as possible. So what we can do here is actually look at this and notice that there's a common factor. So if we divide everything by 5, I'm going to take one line to do it. No work. This is going to be a 2, negative 1, negative 6, 3. Right? Yeah. And this now becomes a 5 times that. Right? If we divide that by 5, it has to go somewhere, so it's going to go there. So now we have a 5x plus 3 term, which is going to multiply at the end. Marking is worse than teaching? Agreed. 100%. If I could get my hands on a grater at any point, I'm sure I would live a much more fulfilled life. Okay, and the other one we had was a 1/2, which should be x plus a half. We'll deal with that later. So for right now, it's going to be a 2. It's going to be a half of that is 1. Add it is a 0. Multiply is a 0. Add is negative 6. multiply by half is -3, add is 0. Again, this has a common factor. We can divide everything by 2 and instead put that at the front here. 2 times all that. So then we say, okay, it's not going to be that. It's instead going to be 2x plus 1. You are the unlucky grader. I'm sorry. And look, it's great when you, like, actually have a good grader, or you are a good grader. 1, 0, -3. I was never really all that great of a grader, although I gave great feedback. Nobody ever paid attention. So, there's also that. Okay, so this gives us x plus 4, 5x plus 3, 2x minus 1. Sorry, I messed up there. That's supposed to be an x minus a half, which is 2x minus 1. And then we get this thing, which comes down. So this is now the last 3 digits here. This is a constant. This is an x. This is an x squared. So now we have 1x squared minus 3. Again, this is our polynomial. P of x is equal to this whole thing, which is as factored as it can get with rational coefficients. And if we just want irrational numbers, factor it all the way to linear factors, then we're going to break this thing up. And, I mean, it's pretty obvious, but this is going to be x plus root 3, x minus root 3. And if you don't really like it, that's fine. You can... It depends on what's being asked, right? If it's being asked to put into linear factors, then you have to go all the way down to that. If you can't just, like, immediately come up with what the linear factors are, again, that's okay. You say, what is x squared minus 3 equals 0 going to get us, right? Let's pretend it's more complicated than this. Or let's say you're not very practiced in this. This is perfectly fine. Set it equal to 0, we get x squared equals 3. And then that naturally is the absolute value of x is equal to the square root of 3. You might know this better as x equals plus or minus the square root of 3, but I don't allow that crap anywhere. All right. Don't do that. So absolute value has a meaning. State what the meaning of that whole thing is. Yeah, they don't... Most of mine don't read it. The ones who did, I definitely noticed. Because they would always be getting stuff right on the next exam that they didn't on the previous one. Or, like, homework. You know, the homework that uses the previous stuff on the next stuff. They were always the ones who were correcting it and getting it right next time. Small group, yes. I also like small group corrections. You may not be actually saying that, but it's fine. But yeah, when we did like small group corrections, that was fine. There were some people who made a fuss about it because it was like, you know, leaking their private information, you know, their grade on that particular assignment was then known to other people, and that was a problem, right? But I don't know. True, the Khan Academy mastery getting messed up by a single typo is kind of frustrating. When we were doing, we did Pearson My Math Lab We also did Newton, Knewton. We also did CE6 or Blackboard at various points. And then we also used in our differential equations class, the guy who was coordinating the differential equations class used the MAA platform. Gotta remember what that's called. Okay, so MAA platform math. Somebody else might know it. Online homework platform. Web work. There we go. All right. Capitals are actually that. WebWork was a scary platform because it was way more literal than any of the other ones. So Pearson, my math lab, and Newton were able to at least interpret some of the answers because they also had people who were on the back end, like mathematicians and math teachers on the back end who were trying to make all of it work. And so it was like, okay, look, if it's close, if it's within this percentage, accept it. If it's like, you know, if it's formatted like this, and then they put in some math stuff, and it could actually plug in numbers into the variables to double check that you've got the same equation, essentially. And I liked that stuff. That was good. So, like, is it mathematically equivalent? If it's not literally character for character equivalent. Some of your students think you're a third-year undergrad. Yeah. I really kind of wish that I'd gotten more involved in, like, you know, research or other aspects of the education department that was there at the University of New Hampshire, or maybe just the math department. Our applied math department ended up releasing an MP3. Releasing, I don't remember if it was MP3 or if it was like one of the other adjacent file formats. But yeah, the applied math program at the University of New Hampshire in 2003, I think, released. Oh well, couldn't have been MP3 if it was 2003. Anyway, like they invented a new audio compression software, which then allowed for polyphonic ringtones. So like that was them. And if it wasn't only them, they were part of a research group, but nonetheless. They ended up patenting it, and like all of the students who were working on it at the time got a share of some kind or another. So it was just absolute bonkers. You were almost a baby. Yup, I was getting close to deciding what my graduate program was going to be, and we had a presentation from the applied math department, the pure math department, think engineering, and physics, and like there was a whole bunch of people coming through and being like, you know, you're math people, you're good at all this stuff, so come on over and play with us. I really wanted physics, but at the same time, I knew I was going to be teaching teaching mathematics at the high school level at that point. So a lot of the presentations did not have anything to do with me. But it was a nice time to just kind of sit around and listen to the other people in my class. have all them get excited about stuff. Jasu, was that an entire class of 10-ish, or was that like your breakout TA session? Because I've had both of those instances, and like having 10 in a class is awesome. You get so much done. Like, even when a few people are dragging because they just don't understand, like 10, and that's it? Oh, man. So great. Comprehensive fundamental checks every so often for maths. Yeah, well. That's what your like initial assessments in each new class are really supposed to be about. I do know that I worked on a team. This was part of the Gates grant for the University of Maryland, Baltimore County. So UMBC. So they had a bunch of the community colleges come over, and we all worked on basically the initial idea of the research project that my associate dean had been placed on. I've been placed on the project. His, like, the little precept that they give you at the beginning was basically want to align all of the precalculus classes across the board. And the problem was that our precalculus classes as community colleges were not being accepted by University of Maryland College Park, which is the big school. And if you don't have your class accepted by College Park, like, what are you doing? Since so many of your students are going to go to College Park, like, you have to have alignment. And so there was a lot of like, oh, well, you know, the community colleges need to get on board. And so all of our community colleges came together at University of Maryland, Baltimore County, which is a, like, it's borderlining on a STEM research institution. It's real close, if it isn't explicitly. Nice, workshop groups, yep. So our we all showed up on like the first, I don't know, 5 meetings or something like that. And so the associate dean appointed me and was basically like, I want you to get involved. And I was like, all right, cool. So when I got there, there was a whole bunch of talk about like, well, you know, the community colleges need to get on board with all this other stuff. And we were like, no, hang on. Just one second. College Park went, and, you know, no massive, like, disrespect to them. They're a good institution. But they changed the requirements for their pre-calculus program. Because we have, you know, our community college had intermediate algebra, which was a developmental class that allowed you to then get into pre-calculus or to college algebra or to like the non-majors track, which generally speaking means that you are in you know, non-science majors track, which meant that basically you're doing either statistics or math literacy, one of those two. Cool classes, definitely do not prep you for, like, you know, doing science. Statistics does, but not, it doesn't prepare you to, like, do the, lab sciences. You have to have algebra. You have to have usually calculus too. Sorry, usually calculus, comma, as well. So, pretty much any lab science, if you're also doing statistics, you're also going to be doing, you know, either capping out at pre-calc or maybe capping out at calculus. Trig, like your second semester of pre-calc. And so we were like, no. College Park changed their requirements on us, and they sprung it on us in like an email that was like, hey, so, you know, just to let your dean know, because it was addressed to the dean and the dean only, you know, just to let all you deans know that we're no longer going to be accepting your pre-calculus class because, and they listed the following. So our problem was that our Precalculus 1 class, which was function analysis, did not include any trigonometry. Let that sit a minute. Because they did like right triangle trig. You know, basic sine, cosine, tangent for draw a triangle, now do some trigonometry on it. And so I was kind of like, what are they doing? And our, at the time, pre-calculus coordinator was like, all right, this is absolutely ridiculous, but we have to do it because College Park is doing it. So we're going to like flop a couple of subjects. Our what was it? Complex variables is all going to be pushed to trig. Or complex, the complex numbers was all being pushed to trig. We were only doing real polynomials, which, like, if you're studying quadratics, why are we, no, why? But it was just to make room because we had to do, you know, basic right triangle trig in Precalc 1. So we did all this tap dancing to get everything in place, and when we got to this meeting at Baltimore County, you know, they sort of like accused us of not meeting the requirements, and we told the Baltimore County people exactly where College Park could stick it. We're like, no, this is not acceptable. And so we had like 5 meetings where we were trying to figure out what the actual requirements for our pre-calculus courses were. And we did all this like alignment of variables and things like that. And then we went, you know what the problem is? We don't even have consistency across the board for calculus either. And so we went through all of the calculus requirements and made sure that all of those were aligned. And then this is like 2 years later, we're trying to develop a web application that is like your day 0 quiz that you do for the calculus classes at all of the colleges across the board. So all of us, College Park, all of the community colleges, and and Baltimore County. So then we pushed it out to the state of Maryland and said, you know, this is something that we're doing just to let you all know. If anybody's interested, you can use it for your day 0. Like, basically, it's a placement test to make sure that you actually belong in Calculus 1. Or, if you fail it, these are the topics you need to work on in, like, the next week. You'd better get it figured out. You know, here are some resources on campus, that sort of thing. So we sent all of this stuff to all of the students in every single calculus class across the entire state. Anybody who wanted to use it, we weren't going to require it or anything like that. But, you know, at my community college, we were like, I think it would be a really good idea if you did this. And then all of our calculus classes did it. You know, certainly all of the full-timers, probably most of the adjunct faculty too. So we got like pretty high compliance in hours. That was for a few years, and then kind of tapered off, and people lost interest because it wasn't a new thing. And then eventually the platform went down, but you know, we did what we could. But it was a good few years that we had where we were working super closely with the community colleges and Baltimore County, University of Maryland, Baltimore County, and we made a lot of friendships. And like the people who were there, like I'm not in contact with them anymore, but in 2015 we did a NCTM. Nope, not NCTM. AMATIC. That's the American Mathematical Association of Two-Year Colleges. We did a session. And so I was like, this is my second AMATIC ever, and I'm super excited to be here. And I'm presenting, and I'm in New Orleans. Like, this is nuts. It was so great. And I went there with one of the guys who was... well, he was my direct supervisor, but he was like basically my best friend. So... So we got along great. He eventually became dean, and then there was a little bit of a awkward rift between him and a few people in the department, and he eventually left. But it was too bad. But he had to make some policy decisions that were unpopular, and then he also said a couple of things that he definitely shouldn't have said, and he was just, you know, there was a lot of noise about it, and then at the end of the year, he was like, all right, I'm gonna walk. I mean, it was a really good time to like learn stuff. You can tell by my exasperated sigh. It seemed like he was trying to toe the line more than he was trying to get our understanding and opinions up to the administration level. Now, maybe that's just my perception and that's not 100% accurate, but you know, the policy decisions were what they were. And I think he was put in a bad situation by the upper administration. And he was trying to, you know, implement these things while at the same time not blatantly call them out for being absolute bullshit. Because they were. Well, a few of them anyway. There was also an administrative award that, like, you could basically, like, a bunch of local businesses had earned this award over multiple years, and like it's a like a bonus accreditation. If you can get this award, you have done really awesome stuff with your business. And so our president was trying to get this award because it's very prestigious and all this stuff. And then, like, as soon as we did get it, because we did get it, it was like the next year she retired. But the worst part about it is, like, every single time that you apply for this award, it's $30,000 or more. And we're like, how many full ride scholarships could you afford to have done for these past like 10 years while you've got all these accreditors coming in and trying to like get us this thing? Maybe just it wasn't quite as bad as he made it out to be. But also, like, I was also not privy to all of the issues that were going on, naturally. Yes, yes, it was that much money. To apply to get this particular business award, you had to pay upwards of $30,000. And like a number of us were just like, this should never have been done in the first place. Like maybe you could have gotten the requirements 1 year and then like done a self-assessment, and then when you think you're above it, then maybe go for another one. But like it was like, I don't know, 5 years that we were applying for this. And again, how many full ride scholarships for people from our county, for people in the city, right? Like people in the city who come and either live in our county or commute to our county. How many full ride scholarships could you have afforded for those individual students and change their lives? How many loans could you just wipe out entirely? It was just absolute nuts. I mean, probably. In a literal sense, you do have to actually pay for like the time of the people who come to your school, because they're there for like 4 days straight. And it's like a panel of 5. So I mean, you're paying for 20 working days of people who are probably, I mean, they're also probably earning executive level money, but let's and then they're doing like, I don't know, tens of hours outside in order to write up their reports and submit them to you, and doing like pre-assessments, looking up your college online, well, your business, because we were really the only community college who was ever going for this. Yeah, I had opinions. And then when we got a new president, she came in and, like, it was all hopeful for, like, the first 6 months, and then she started making some super, like, weird, kind of authoritarian policy changes, and we're all just like, what are you doing? And then, when I was leaving, our entire department and like all of the other departments met at the local library and unionized. I was like, oh, if only I was staying here, I probably would have. I mean, honestly, if I was, had I stayed there, I would. Got what? The award? No. Like, the award is a business proposition that, you know, your customer care and your other teams are all working to a certain efficiency level and all this other stuff. And like, how happy are your customers and that sort of stuff. So there was a lot of behind the scenes stuff that they were working on. But no, had I stayed there even another year, there's a good chance that I would have been telling everybody to put me on the put me on the union team, because like it was that bad. There was a lot of stuff going on that was not going well. Okay. Maybe I could actually do the thing I set out to do at the beginning, but you know, whatever, it's fine. Dividing complex decimals? Ooh. Yeah, no, that's fair. What kind of thing are you doing? Like divide by 7 or something? Okay, so like I said, what my father was looking for was something like this, where we were saying we've got a triangle that's been rounded off at the three corners by circles. They are tangent to the point where they come in, and the size doesn't really matter because you could decide how big these are. They could even be overlapping. There's a whole bunch of stuff you can decide. Now, for his purposes, what he's doing is keeping them separate, and then the intervening area is going to be curved inward. Yep. So that one's actually pretty easy if you think of it in terms of scientific notation. Right, 1.21 times 10 to the 0 times 4.3 times 10 to the negative second. Right, or you put it in, this is not English notation, but right, you could put it in a different scientific notation where you don't have any decimals at all. Right, so if you do this, then we get 121 by 43, and also 10 to the 2 minus 3. So 10 to the negative first, and then here you've got, well, what this number is going to be. By the way, Vedic mathematics, using the Hindu Veda as your instruction guide, says that what we do in order to get the ones place is to multiply your ones by your ones. So 1 times 3 is 3. What you do to get your tens place is ones by tens and tens by ones. So we multiply our 3 by 2, or rather 3 by 20, and 1 by 40. So 40 and 60 is going to get us 100. Carry. In order to get the hundreds place, we can multiply ones by hundreds. Hundreds here is 0 by ones, and also tens by tens. So here we get an 8 plus 3 by 1 is 3, so, and a 0. But that's going to get us 11, plus the 1 from before is going to get us 12. So 2 here, carry the 1. And in order to get the thousands place, we need to multiply, in this case we've got hundreds by tens. Right, and that's going to be the highest that we can get. We don't have any thousands places, so we can't multiply by the ones at all. and we don't have the other tens by hundreds. So this is just going to be 4 by 1 is 4, plus 1 from earlier is going to be 5. So 5203. 5,203 by 10 to the negative first. So therefore, 520.3 should be the answer. Wow, that is really messed up. Where'd I go wrong? Oh, that's a negative, isn't it? A negative fifth. There we go. Oi. I do math. Speaking of reviewing basic math. Yep. Fail to see where you went wrong. Absolutely. So my initial impressions on my father's problem here were that, one, we could use a catenary. So in a catenary, we're basically pinning 2 points to the circles and then letting a weighted chain or rope get weighted by gravity in between them. So would be a super easy way to like be able to trace that line and then be able to say, okay, this is the shape I want for the curve. Okay. Alternatively, I said we could do parabola, right? Parabolic. So it tends to be a little more steep. We're just about to go to an ad break, but I'll explain this. It'll go in like a parabolic sort of shape, and then see what we can do with that. Or we could do something like sinusoidal. So we could get like a little bit of a cosine curve or a sine curve and make that in there. And there were, I think, 2 other candidates that I wanted. So I'll come back and explain that in 3 minutes. See you in a bit. Alright, we're back. So I had a couple of ideas, right? So what I'd done was that first thing I said, if we could set this up and say, like, our two circles for just the bottom, right? I put a few like mock-ups and just said, okay, if we do just a few things like this, like y minus 1 and x plus 4. Right, so it'll go out to the edge and hit 5 here. Right, negative 5, 1. And then also on the other side, positive 5, 1. So I want this to be symmetric, make it easier, all that good stuff. So we Control Z. Everyone's favorite friend. Okay. We copy this, we bring it down, we do it again, but this time we make it x minus 4, so it goes to the other side. And keep it the same color. Oops. Right, so the initial amount here is that we're going to have something that goes from like negative 6 to 6, give or take. Right, so this is going to be like it's supposed to be a equilateral triangle that we start out with. So like this is the initial block of wood that we're taking. The amount that's going to be cut off of the corners is just going to be rounded to the circles. So that's easy enough. We don't have to worry about that too terribly much. The problem is, like, what kind of curve are we going to put in between these things in order to make it smooth, have the depth that the client wants, and you know, be aesthetically pleasing. So I was like, okay, we can do something like a cosh function. So this is the hyperbolic cosine function, which overall right, so a hyperbolic cosine looks like e to the x plus e to the negative x all over 2. Do you trust an interesting YouTube video that has 900 views and 300,000 subscriptions on the channel? How old is it? If it's from the beginning of the channel's life, that's not really all that surprising. If it's from, like, yesterday, yeah, 4 hours, it probably... people just haven't had a chance to notice it. I mean, sometimes videos are out for a week and I don't watch them. Once the new goes away, then I'm like, oh, well, guess I haven't watched that one, and I usually watch everything from this channel, so, you know. Yeah, that sounds like clickbait. What's the channel called? Cosmos Labs. Okay. It's not one that has been flagged that I know of. Okay. This is one that I am going to highly recommend. Yeah, stock material and voiceover. Yep. So that video right there, anybody who isn't clicking on it already, is by Kyle Hill, and it's called the Science Spam Crisis or something like that. So basically he's calling out all of those particular channels that have, you know, ridiculous number of subscriptions. Everything that it makes it is basically just an AI dump of nonsense, plus a whole bunch of stock footage and stock photos. So that is actually a very good watch if you want to see like precisely how Kyle Hill, known YouTuber and former scientist, or at least highly science-trained individual, goes through and just notices, like, you know, all of this stuff is wrong. Yeah. So anyway, what I did was I said one of our options is going to be a hyperbolic cosine function. So it uses e to the x and e to the negative x in order to come up with something. And then I was like, okay, well, if I want to make it, you know, in the correct direction, we're going to shave stuff off going in this direction, then it's going to be down here. Then we're going to want this to be higher. So first of all, this is going to be like +2 to get it up into the proper range. And then we need to make this multiply by like 0.3, 2, 1. Okay, that's too far. So 1, 5, 1, 6, oops, 4, 3, yeah. There you go. Looks approximately. All right, this looks approximately like a. Oh, you know what? Hang on. Better one. Instead of there, fix it here. Inside, because this does a horizontal compression. So we're going to allow this to multiply out without changing this point. So it'll still go through 0, 1, right? So it'll go through at the same level as our center points for these circles, and that won't change. So if we do, like, again, 0.5, 0.4, 0.3, 0.35, 3.6, 5.8, 7, 5, 4, 3. Okay, so somewhere around here, we get pretty close to tangent against those circles. And so at some point this is just going to go up and look like it's a continuous, like almost straight line until it goes into the next one. So like this is the sort of thing that I would want, me personally, if we're trying to join two curves together. Now I grant you, this is like, my dad's a woodworker, so a lot of this is going to be eyeballed. right? Like, we can draw these nice curves and everything. But realistically, we're just going to get close. Okay, so this is going to be somewhere around negative 3.5, comma 0.135, 0.136, whatever we want to say for this, whatever it's going to end up being. Right, so these are the values that we're going to get approximately for this hyperbolic cosine function. Now, I'm not sure what kind of curve the client wants here. If this is the kind of curve that they're looking for, it's an option, right? So, other option, we could put the vertex at the exact same point, vertex of a parabola at the exact same point. So we can make this a negative parentheses, no, we just want x squared, right, plus 1. And then again, what we want to do is multiply our x by a smaller number to make it expand out without moving anything else. So this is going to be, again, 0.2, whoops, 0.2, too far. So 0.3, 0.29, 0.28, 0.27, 0.26, okay, 0.265, 0.266. That's pretty close. That's about as close as we're going to get. Right, so this and that are going to intersect at like 2 points in here. Oh no, that's also the other intersection with green. Okay, so red and green intersect here. Oops. And here. Red and purple. So we want to bring those closer together as much as possible. It's pretty close in terms of like... There you go. That's pretty good, right? It's put these 2 points intersection with purple as almost 1 point. So this is negative 3.55, give or take. So that's another decent approximation. It's also different, although not really all that much different from green, at least within the bounds that we've selected. So what do we do in terms of like, you know, how do we get the hyperbolic cosine function? Well, that's actually pretty easy. You take this whole thing, you flip it upside down, and you hang a weighted rope from 2 points. Where are those points? Well, we just found out where they should be on these circles. So we could get those coordinate points, we can approximately pin that up, and then change the amount of rope that we're hanging between these two things until it hits the appropriate location at 0,1, whatever that means in terms of like, you know, real inches, because he is doing this in SAE, not metric. It's not my problem. Okay, so green is real easy to do when you actually like make it. Red, the parabola, is actually not all that super easy to make. You really should know where your focus and directrix are, and then you can figure out where is the equidistant point to the directrix, making a... now he has tools to be able to do right angles and all that, so that's easy. So we make a right angle, drop it down from the directrix, and then we find out from the focus where we get the exact same distance along the directrix to point as we do from focus to point. Where those two lines end up meeting, we put a point, and that is a part of the parabola. Right? Alternate ways to do this are like, you know, get a mirror of a good shape that you want and shine it down on the board in such a way that it's going to make a parabolic shape to it. I mean, like, it'd be ridiculous, right? There, you could do all sorts of things to make this happen. Using a focus point in directrix is probably the easiest way. Unless you just want to literally take this piece of paper and print it out and put it on the wood, which is always possible. Right, so I suggested either of these is fine. Like I said, we could go with like a cosine function. And leave it there, and then do this by 0.2, 0.4, by about 0.41. Making a cosine curve on the actual wood is going to be a little bit more difficult, so I don't know how to do it nicely. It's going to end up, in this case, just being like find individual points, make it work. I think that does it. Put about 0.41 foot. I know that number. Oh no, that's 0.707. Never mind. Minus 1 parentheses. Shut off these other ones. Oh, it's real close. I think that's a coincidence, but man, that is so close. Anyway, I think it would be hard to draw a cosine function without, again, just getting the points or tracing it on a piece of paper. I don't think there's an easy way to just say, like, here's a physical way to make a cosine. All right, see you, Jamie. Good luck. I don't think there's a nice physical way to make a cosine in the same way that you can make a hyperbolic cosine. Even a parabola, right? Fairly simple to make these things work. Not entirely sure how to make a physical parabola that would be better than finding where the directrix and focus are. Which, again, that actually might be an interesting point, is we could start with a focus point and a directrix and then work out mathematically where would you need to put a directrix in order to make like a focus point at 0, 0, make a proper curve that's going to touch both of these circles tangentially. But anyway, we got a bunch of options here, right? And the other one, and again, our cosine curve here is like within the kind of error that you could probably reasonably make with hand tools, even power tools. You know, any more accurate, and you're going to need a freaking laser cutter. Like, if you want it this precise, you're just not going to be able to do very well. And then the other option that he was thinking, and he came up with this, and he said, what if I were to create then new equilateral triangles off of the sides of all three of these equilateral triangles, or the sides of this equilateral triangle that we're making. Then from the far corner point, we just sweep a circular arc that goes through the points of our circles. And I was like, yeah, I mean, that's definitely something that you can do. The only problem with that is that if you do that, we're going to end up going through the circle at some point, and like our line will no longer be tangent. And so you're going to have to just kind of eyeball it. And he was like, yeah. So I broke out my trusty set of awesome math tools. So my compass, straight edge, and ruler. Straight edge ruler. And I was like, all right, let me see if I can get this right. And I did a couple of iterations, finally got it right. I don't think there's anything. Yeah, there's nothing important on this. So I was like, all right, it's going to look something like this, where we're going to get either we could sweep out arcs going from so we take like an equilateral triangle built off of here to this point, and then we sweep out a radius that goes through the tangent points to the line, our blue line and our purple circles. And that's going to be this close one. And I said, okay, now let's just like flatten out the curve a little bit and get like a nice sweep that goes from the circle into the arc going in the opposite direction. So the curvature is all messed up, but you know, it's going to work-ish. And then the third one I picked was take a radius from that equilateral triangle that we built up to here, and then sweep that through the point that goes through the corners of the main triangle that we started with. And so that ends up getting us this line here, and then we darken it up in the middle, and then we again make a nice little curve that goes from the circle down to that part there. This is probably not going to work, but all right. Something that looks like that. Right, so we make that nice little curve, goes from the circle into the arc back up to the other circle. It's very steep because it has to go through like a lot of the space. And then I said, okay, I don't like either of these for multiple reasons. What if we picked a point that was halfway in between the tangents of the circles and the edge of the triangle, like the vertex of the triangle? So measure out that distance from the vertex of the triangle to the tangent of the circle, and then just have that distance. And that swept out one that went like this. And then I, again, swept out most of the arc in pencil, and then did a quick little bump that goes back out to the circles on either side. And so when I showed him that, he was just like, yep, that's exactly what I wanted. I was like, all right. And that's the other thing, is that like this one is also very easy to do, right? You just need a little extra space, and you need a compass. And he's got compasses, right? He's a woodworker. He knows how to work with compasses. I'm like, all right, that's fine. The only other, right, the other option that I was kind of hoping he would go for was the catenary, where if he used some sort of rope to make this hyperbolic cosine function, I think that would just end up being easier in order to physically do it. It doesn't involve all this other stuff with, you know, compass and messing around with things like that. It's just basically you stick two pieces of a rope at these points here. Right, stick two pieces of rope at these points here, turn it upside down, and let it hang, and see how far you want it to go in. That's it. So, there were some options, right? I gave him I gave him 3 options on the circles. And let's see, what would that be? The center of this circle would be at it's the height of the equilateral triangle. The equilateral triangle currently, yeah, damn. Like, I could do this. It would not be that hard, but it involves calculus. I was trying to figure out where the line that has a 60-degree angle will be going through. If it has a 60-degree angle this way, that's 90 degrees to the center. So it'd be, should be here at angle 2 pi over 3. Right? And then the slope is going to be 60-degree angle. Tangent is what, root 3 over 1? So like y equals square root 3 x plus 6. Ugh. Nope. X plus 6. Right, give or take. Minus 1, 5, 4, 4, 5, 4, 6, 4, 7, 6. Nope. Right, less. This is also how I did some math research in the past. Right, so if we do something like this, right, we'll end up getting a pretty decent approximation. Okay, we could also mess around with like just having it be just root 3x plus whatever we're going to get in order to make this tangent show up. Again, approximate values, but here, this is also an important point. That's our value now for the length of the equilateral triangle. It's going to be about 11.46. Which also was approximately the correct value that he wanted for how long the initial piece of wood was. So he said it was going to be like, 10 to 12 inches, give or take, from an equilateral triangle getting shaved into this rounded, again, circular triangle around the corners. And then we need to bump in the middle to make it some sort of curve. Okay, so we know what this is going to be now. Again, our square plus squared equals, 11 point, what do I do? 11.46 squared. Right, so that's approximately what we're going to get. This is going to end up being, again, this is just x squared, and this is going to be y plus 11.46. Nope. Right, so we need... That got us back to 0, right. We need this to get us to the intersection point. Over square root of 3. And this is going to be 2 times that. Nope. Damn it. This was going to be in there. Yeah, no, it's just the same place. I knew it was going to be the same place. I just need to double check. Alright. Yeah, close enough. Alright, so this is one example that was given. Again, going to the corner of the triangle. This is second choice was shrinking this distance until it reached tangent with the circle. That's not actually true. It only reached the there. So that reached the bottoms of the circle, and I said, you know, we're just gonna end up ignoring everything outside of here. So we cared about only those pieces that were between negative 3.34 on both sides, right? Positive and negative. So if we did this as x is less than 3.34 and more than negative 3.34, right, that's what we get here. And same with this one. It's going to be between horrible negative 3.02 less than x less than 3.02. Right, or take the intermediate, which is going to be between the two, which I think the radius is just going to be half as well, because these are linear distances, so or half the difference. So going from what, 10.68 to 11.46. This is also going to be the same stuff, but then we say here, this is going to be, let's go like this, 11.46 plus 10.68. Let me take all that and divide by 2. Ay. What do you know? It's halfway. Messier things have been done. Right, and then we're going to say again, this is going to only be between these values. So negative 3.03 and positive, that's symmetric. So negative 3.03 is less than x is less than 3.03. Right, so these were the three options that I sent over and said, you know, if you're going to make something like this, then these are some pretty good options in terms of making a curve. Obviously, this one requires almost no like rounding off at the end. Basically, my recommendation was to leave a little bit here, and then it tapers off a bit there. Or this one, it's going to like taper off here, or like here, and then connect down this way. And if it's this one, it's going to have to like have a really long taper. So it was an interesting exercise in order to figure out like what are we going to do in order to figure out how to make this thing work. Miniature engineering project that I have no idea how to actually do. Okay, random other question. What is 6 root 3? Alright, square root of 3 all times 6. Alright, would be 1039 minus 464, 104, 1, bunch of other stuff. 9.9282. It's not really satisfying. It's not like any particular number, but alright, so now you know how OB solves problems when real stuff's involved. So another option could have been if we'd gone and used GeoGebra. Right, we could pull up tools. So circle with center through. Again, in this case, if we, what did I do? -4, comma 1. Nope. Ah, there we go. Yep. Okay, so we line up these points. Again, circle with center. Again, -4, 1, and then stretch out to -4, 0. So this is the other benefit of using GeoGebra, is that like it has geometric tools that we could just construct. We can make a line, just line right between here and there. So that's just gonna make a line. Now, if I want to make an equilateral triangle, right, then this is going to be slightly awkward. Because, in theory, I won't know how tall this needs to be. I do know that the distance between the points on the circle that are tangent circles that are tangent to that particular side. So if I make a, again, 60-degree angle going this way, that's also a good point, right? So angle. Oh. Oh, does it? Okay, no, never mind. Undo. Oh, redo that one. Okay, so angle with a given size. Select leg point, vertex, then enter size. All right, that's going to be a slight problem because I don't know exactly what it's going to be, but that's fine. So we want a 60-degree angle counterclockwise from this particular position, and so that's going to get us B prime. Right, so now, oh boy. Tangent, how does this work? Select point or line, then circle. Yeah. Polar diameter line, no. So we want a tangent that has this given angle or is parallel to that line. That's going to be the problem. Construct a line that goes through those. Construct a parallel line. That's the problem, is I don't know. Line that's parallel here, but connected to... That's not what I wanted. What is it? Select parallel line and point. Have to have a marked point. Wait. Hang on. Move. Move E. Like... It's so close. Alright. It's ridiculous. Alright, I know what I want. I want this to move E until B prime is on circle A. Or to create a parallel line that is also a tangent to the circle. Ooh. So, like, that's one. Intersect of those two things. Right? Why are those changing? Okay. Oh, there we go. Yes. Okay. Okay, find the intersect between here and there. There we go. There's G. Okay, so I get move view. All right, delete this. No, I want you to keep that. All right, I want you to delete E. It relies on those, maybe. Yeah. Okay. So now we need to go do the same thing on the other side. So we need to find an angle. Make an angle with given size. Leg point, vertex, clockwise 60 degrees. Make a line. Could be a segment. Okay, and then tangent. Select a line. Bingo. Okay. Whew. Alright, is there a way to just hide stuff? Because okay. Then this also shows us where the circle has to be. Is it just 8? That seems wrong. Circle with center and radius. Radius 1. No, it's not. That's weird. Wait, are these radius 1? Where are my things? Table? Nope. Spreadsheet? Nope. So color, name, value. 40. Show value. Or 1. Yeah. Okay. So those should be. Oh, because it's not actually at 8. That's why. Okay. That's actually okay. Makes perfect sense. Shouldn't be at 8. You're really close. I would like you to draw me a circle, which have 4 tangent points at the following locations. Oh no. Conic through 5 points, though not obvious. Lips, slick foci, and then okay. Yeah, no intersection between those because it's really close, but it's not quite right. Right, what about the intersection between that and that? Yeah, I got 2 points. Oops. Yeah. So close. Okay, so we're gonna just delete the... Okay. And then we're gonna hit circle with center through. With radius. Okay, so we go like this, we hit 1. Then we say that the... No. Settings. Algebra, scripting. Okay. There's no way to actually change what its location is. Not sure there's even a way to specify what the center is. Used to be a way. There used to be a way to go in here and like check all the values that we plugged in. So like, you know, the stay on page. Stay on page. So there used to be a way to like check the value of this number, and then if it's wrong, just manually input it differently. At least I thought there was. Nope. Definition. Definition point I. Okay. Okay, so point I. Okay. All right. Let's try this then. We're going to put a point at 8, 0, and then we say no. We don't actually want that there. Definition. 0, comma. All right, let's just test. Cool. All right, 3.5 works fine. What about square root 3? Nice. Okay, so this does work. So the center point of this particular circle should be, again, the size of the full triangle, which goes out to where tangent G is connecting with that circle. It's going to be twice the total distance. Well, no, okay. That value is going to be our horizontal distance. Vertical distance should be root 3 times that. Root intersect. Okay. Give me that number. No? Alright. Of course not. That'd be too easy at that point. Alright, ads are going to start. I'll be here. See you in a couple minutes. Alright, let's try this. So we're going to try going back up to J, changing this number from 5.73 to this number, 4.577. That's going to get us through the middle, which should, in theory, get us circle, center, and radius. Center at J, radius of 1, and that looks tangent in all of those cases. That looks way better. Okay, this line, if we delete this line, does it kill everything? No. Okay, good. If we delete this line, yeah, it does. Okay. So, I'm gonna set this for dark blue. Set this for dark blue. Set this for dark blue. Okay, now we can actually see the triangle that we're supposed to be getting. Mostly. Okay, I can be deleted. We don't have a reason for that. Perfect. Alright, so we did get all 4 of those points. Exactly the way that we said it was going to work. Why theta? Not n. Anyway. Okay, so it is a point as a focus, and then a directrix. So what if we wanted, I'd suggested this earlier, right? If we did a point here, and then points here and here, which then make a line. Then we use those as the focus directrix. Oh, goodness, no. Okay, let's move this up. Should do something. No, you cannot do that. How dare you? We can move the directrix. We are not allowed, under any circumstances, we're not allowed to move the focus. Okay, so if we wanted to, we can move it kind of like absurdly large. See what happens. Somewhere between 3 and 4. We reach the value we actually want. Alright, if we maintain that 0, 0 should be the focus, then the directrix needs to be somewhere around 3.7, 3.6, 3.7, in order to get our parabola to correctly intersect with the circles. Well, makes it interesting anyway. Okay, let's go over and see. Xandorific is one of our friends from the old Geek and Sundry days. He's been working on a bunch of stuff right now, doing a creative writing workshop. So go over and see his stuff, and we'll be back maybe tomorrow to do some fun stuff. Definitely on Friday for gamey type things. So we'll see you in a day or two, and hope you all are having a good rest of your week. Let us know over on Discord if you have any questions or anything you'd like to talk about otherwise. We have our groups here, affectionately known as the Math Chads. Oh no. Oh. Uh-oh. Well, our bot seems to be down. But anyway, we'll see you all later. My name's Obi-Wan Piz. This is N Simplex Pachinko. Have a good night.